So I've decided to put this lecture online in video format to make it easier for you to be able to grasp the material. There are many students that have some difficulty learning or recalling how to do some of these calculations. And I also realize that many of you will grasp the different concepts that we'll talk about in today's lecture at a different pace. So when I talk about this lecture in the classroom, then I'm typically moving faster than some would like, and then slower than others would like. And so there's some students who think that I'm moving too slow. I'm trying to move at a pace that's good for everybody, but it's just impossible for me to match the pace of learning of everyone. So here is my suggestion for getting the most out of today's lecture. First, get the PowerPoint slides from Blackboard so that you can follow along. I'll be walking you through the steps for doing various calculations today in class, and it'll help you if you're able to see my original PowerPoint slides. I'm also going to suggest that you do this as a group. So in a group setting, in a small group setting, you're going to be able to help each other work your way through some of the calculations and some of the concepts that we're going to talk about today. So perhaps if one of you is not understanding a particular concept, there's going to be another student that will understand, and you'll be able to help one another. Throughout today's lecture, I am going to periodically pause. Now I'll pause and I'll give you an opportunity to answer a question. Here's my really, really strong encouragement to you. Do not just fly through the video to get through the entire lecture. That is not going to help you be able to learn the material. When I ask a question and then I say you should pause, then actually pause the video and see if you can come up with the answer to the question. And then press the play button and see what the answer is and see if you got it right. And that is really going to help you to be able to solidify your knowledge of the material. After you finish watching today's lecture, then try the practice problems that are on Blackboard so that you can practice and build your skills. Now, you must master these concepts and the concepts and calculations for control charts before coming to our next class, Class 15. So Class 15 is a review, and in that review, I am going to be going through all of the calculations that we have gone through for this section of the course that are needed for the exam, but I will not have the time to be able to fully explain how to do all of the calculations. Obviously, we've been going through 2, 3, 4 different lectures and talked through a lot of different material, and so I'm not going to be able to squeeze all of that learning into one class session. So do your best to master the material before Class 15. Then I will go through some additional unique problem types in Class 15, and that will be a great review for you as we get ready to move into taking the exam. All right, well, if you're ready, then I'm ready. Let's get started.
But what about you? Are you normal? Well, a common way of defining normal is to say that something about you is normal if you fall within just one standard deviation of the average for all people. But there are a lot of things about you. You can easily think of, say, 36 different independent variables, different things to say about yourself. For instance, how tall you are, how many friends you have, how bad your breath is, or say, how often you lie. Now, the statistical probability that you would be normal for all 36 of those different attributes is actually 1 in a million, which means mathematically speaking, it is quite abnormal to be normal.
So this is exactly what we are going to be able to do today. We are going to be calculating probabilities for certain events happening if we know what their distributions are. And I know that you have seen some of these calculations in the statistics class. I also know that you probably don't remember a whole lot about how to do them. So I'm going to start us from scratch and make sure that everyone is on board with this. Students have told me in the past that I do a really good job of teaching the statistics part of this, and many of them say, I wish I had had you around when I was taking my statistics class. So I really want to encourage you You can understand this. This is a topic that I know that you can grasp, that I know that you can do. And then the neat thing about this, and we'll talk about this later in the class today, is that if you understand how to do these calculations, then you are going to look like the smartest person at your company. You are going to be able to calculate probabilities for certain events occurring, helping some of your managers to make better decisions using those statistics, and feel very confident about your abilities to do so. So let's get started in talking about some of these concepts. All right, for all of our calculations today, let's assume that we're talking about a company that produces 1 pound bags of candies. Okay, so that's what I have on the slide. But if you're thinking about this, you can kind of, when I think about it, I think about M&Ms. Okay, so you know how this works, right? You go to the grocery store and you're walking down the shelves, and maybe it's you have a party and you want to buy a bag of M&Ms. And so you look for the big bags of M&Ms and you see the 1 pound bag. So here's what I want you to think about. If you're watching this as a group, here's what I want you to think about and talk about. When you look at the bag of M&Ms, how do you know that it is a 1 pound bag? Okay, go ahead and pause the video, and I want you to think about that and talk about it. How do you know that you have a 1 pound bag in your hand? What do you see? Okay, sure. The bag has a label on it, and the label says 1 pound. So you pick up the bag of candies, and the label on the bag says 1 pound. So you take the bag home, and let's say that you have a really precise scale, and you put that bag of candy on the scale. Now, here's the next question I want you to deliberate as a team or as a group if you're watching this video. When you put that bag on your really precise scale, how much does the bag weigh? Okay, so hopefully you answered this correctly, and the right answer is not 1 pound. So when you go to buy a 1 pound bag of candy and it says on the label that it is 1 pound, it is not going to actually be 1 pound. Now, the company can do the best job that they can of trying to make bags of candy that are 1 pound, but none, hardly any of those bags of candy are going to be exactly 1 pound. Now, most of them are going to be around 1 pound, but some are actually going to weigh less than a pound, and others are going to weigh more than a pound, because there's going to be variation in the process for filling a bag of candy. So it turns out that the US government has actually established tolerance limits or specification limits for 1 pound bags of candy. So if you are going to market and sell a 1 pound bag of candy and you're going to label it as a 1 pound bag, the US government has set specification limits for what constitutes quality in terms of the weight of that bag. And of course, it's not just one number, it's a range of numbers, but it gives a minimum and a maximum that the bag can weigh and still be considered a 1 pound bag of candy. Now, the US government has no idea about your manufacturing processes or your process for filling a bag with candy. The government doesn't know whether or not you can meet their specifications, and they don't really care. All they want to know is, are your bags of candy meeting these specifications? And if your process is capable, then you probably don't have to inspect your bags of candy. They are just going to be within those specification limits. But if you are not capable of meeting the government specifications, then you're going to have to weigh your bags of candy and inspect them to make sure that they are within the allowable limits before putting them out onto the marketplace. So that information about the government specification is given here in the NIST Handbook number 133, Appendix A, Table 2-5, and you can look all this up on the government's NIST.gov website. And it mentions here that for a bag that is labeled 1 pound, so if you have a bag that you're going to label as 1 pound, that the FDA will allow a variance of plus or minus 0.044 pounds. So they will allow it to be 0.044 pounds less than a pound and 0.044 pounds more than a pound and still be labeled as a 1 pound bag. Now, just incidentally, and this is just fun information for you, this handbook has all kinds of specifications for all kinds of things related to food products, including It has a specification for the maximum number of roach body parts that can legally be packaged in a 1 pound bag of candy. And the scary thing is, I will tell you that the specification is not zero. It is a number greater than zero, which the FDA actually allows for a certain number of roach parts, body parts, to be in your 1 pound bag of candy and still be considered suitable for sale. I know, gross and scary. So let's assume that in this manufacturing process that we have a machine that is producing these bags of candies, and we're labeling them as 1 pound bags, but we are producing bags that average 0.99 pounds. So let's think about that for just a minute. Why would a company produce bags of candy that they're going to label as 1 pound bags, but then they set the machine to fill those bags of candy with only 0.99 pounds and not 1 whole pound? Can you brainstorm that as a group for a minute? Go ahead and pause the video and think about that. Okay, you may have thought up your own ideas as a group, but one idea that I think of is it's cheaper to fill a bag with 0.99 pounds of candy than it is to fill a bag with 1 pound of candy. And as long as the bags are still meeting the FDA regulations for the weight of the bag, then the company won't get in trouble for underfilling the bag slightly, as long as it's still within the FDA specification. So that might be a reason why. Now, we're also going to assume that this machine has been estimated to produce at a standard deviation of 0.010 pounds, so 0.01 pounds standard deviation. And of course, that number would have come from calculations that the company did, or it could come from the control charts. Remember, when we calculated control limits on the control charts, we actually estimate what the standard deviation of the process is in order to create those limits on the control chart. So perhaps a company has been tracking their production of these bags of candies with control charts, and so they have an estimate for the standard deviation. So we've got a machine average currently of 0.99 pounds and a machine standard deviation of 0.01 pounds. And the first question that we're going to ask here is this process capable? So let me remind you of the formulas that we have for calculating process capability. So we've already seen these formulas before, and these are the formulas that we're going to use to calculate the process capability. And I've actually given you in the problem statement all of these different numbers. So what I'd like you to do now is I would like for you to pause the video and figure out what all of these variables are that we are going to be using in these formulas. So here are the calculations for the variables that are used in the process capability calculations. All right, so now let's give it a try. Here are all the variables, and here are all the formulas. See if you can determine if this process is capable of meeting the FDA's regulations. All right, so you should be able to plug all those numbers into the formulas and get these numbers. And now we have to choose which one is the process capability. So of course, let me remind you, CP, that's the first calculation up there that's in the middle, CP of 1.4667, that is the process capability if the process were actually centered on the specification. Now remember, the specification is centered on 1, because the FDA gives the specification for a 1 pound bag of candy, and it allows it to be greater than or less than 1 pound by 0.044. So CP is the process capability if the process were centered at 1 pound. But of course, this company does not have the process centered at 1 pound. They have it centered at 0.99 pounds. So we calculated CPK. So CPK is the process capability for either tail of that distribution. So out of these three numbers, which one of these three numbers represents the process capability for this process? So I'll give you a minute to think about this with your group. And as you recall, When we're choosing process capability, we will choose the smallest of these values. So the smallest value is 1.133. That is the one that is going to limit our process capability. And so with a process capability, CPK, of 1.13, that would be considered marginally capable, which means that this company is going to be making a lot of scrap and is going to need to do extensive inspection. Now, there is something relatively simple that the company could do to increase the capability of their process. Can you remember what they can do that would increase the capability of their process at this point? All right, what they could do is they could recenter their process at 1. So currently, they're really trying to make bags of candy that are 0.99 pounds and selling them as 1-pound bags. But if they were to readjust their machine to actually try to make 1-pound bags of candy, then their process capability would move up to this measure of CP of 1.4667. So you can actually try this out. Take a minute to prove this to yourself. For the calculations of CPK, instead of the center of the distribution being 0.99, so instead of using a mu of 0.99, put in a mu of 1. And if you do that, you're going to find that both CPK measures will be 1.4667. And so the resulting process would have a process capability of 1.4667, which would be considered capable and actually moving toward world class or Six Sigma quality. Now, this will cost the company a little bit of something because the company will now be filling the bags with more candy than they were previously. So there will be an additional material cost, but their processes will be much more capable. So let's do our first probability calculation. Now, don't freak out seeing this formula. I know you've seen it before in statistics. I promise you, I will walk you through slowly how to use this. You are going to be able to be a pro at doing this. So first, let's look at the problem statement. So here's the question. The question at the top says, what is the probability of pulling a single bag of candy from a production run that weighs less than the lower specification? Or what proportion of bags produced will be smaller than the lower specification? Now, the reason that I ask these two questions is because these two questions actually ask the same thing. So I can ask a question on an exam and use either of these wordings, and you will know that you're going to need to solve this question the same way. So, I'm not necessarily on the exam going to write the question both ways. I'll pick one of the two ways to be able to write the question on the exam. So first, let's imagine what this really means. So I think it's going to be helpful to you to understand this if you think about physically what is actually happening in the process that's represented by the question. So what this is saying is, let's say that you're actually standing beside the machine and the machine is making bags of 1-pound bags of candy. And all of these bags are going into a big bin or a big box. And so what this says is, what is the probability that you reach into that box and you pull out a random bag of candy? And of course, you don't know how much it weighs. You're just picking a random bag out of the box and you're asking, what's the probability that you pull one bag out and that one bag that you just happen to pick out weighs less than the lower specification that is set by the FDA? Another way of asking that is, if you have the whole big box or crate of bags of candy and you weigh all of them and you put them in two categories. One category is bags that weigh more than the lower specification, and the other category is bags that weigh less than the lower specification. Then what you're asking here is, what proportion or what fraction of the bags that were in that big box are smaller than the lower specification? All right, so that's our situation, and that's the question we're trying to answer. And we're going to do it using this Z formula. And so here's the formula. Remember, this formula will be given to you on the exam. So all you need to know is what the variables mean. So we know what mu means. Mu is the process average, the current average of where the machine is actually producing product right now. And the sigma is the standard deviation. That is the standard deviation of the machine right now. I'll tell you about x here in a minute. What we're calculating is we're going to calculate z. Now here's what z means. All z means is it is the number of standard deviations away from the mean that this observation is. So for instance, if you have a z of 2, a z of 2 would be 2 standard deviations above the mean or above the average. A z of negative 2 would be 2 standard deviations below the mean. So I want you to tell me, if we were to calculate z for our control limits on a control chart, okay? If you were to calculate z for the upper control limit and calculate z for the lower control limit on the control chart, what would the calculation for z be for the upper control limit, and the lower control limit? Now pause the video and see if you can figure this out with your group. There are no calculations needed for this. You just need to think about it. If z is the number of standard deviations from the mean, then what will the calculation of z be for the upper and the lower control limits on a control chart? And your answer should have been 3 and negative 3, because the control limits on a control chart are set at 3 standard deviations above the mean and 3 standard deviations below the mean. That's kind of our definition of a control chart. Okay, but we're not dealing with control charts here. We're dealing with the probability of reaching into that big old box of candies and pulling out one bag, and that it just turns out that that one bag weighs less than the lower specification limit. All right, so let's learn how to use this z formula. All right, now follow along with me. I know that you've got the formula, and I know that you have some of the variables, and I know that you remember doing this in your statistics class. I'm going to teach you how to be able to use this formula so that you always get these problems correct. So I want you to follow along with me. This is exactly how I always solve these problems. I begin solving the problems by drawing a picture. Okay, so if I were doing this problem on an exam, the very first thing that I would do is I would draw a picture of my distribution. So here I have a diagram, a picture of a large pile of bags of candy. So you can imagine I've got all the candies, I've weighed them, weighed out the different bags, and I've got them in a big pile. The lighter bags of candy, they're there on the left. The more heavy bags of candy are over there on the right. Most of them are in the middle, and our process is centered at 0.99 pounds. Now, this normal curve is just on a number line. So now we've got all of these variables, the upper control or upper specification limit, lower specification limit, the average, process average, and the standard deviation. Now we need to figure out what all the variables are that go into the formula. So we have mu, the process average, 0.99, and we have sigma, the standard deviation of 0.01. Now we need to know what x is. So x in this formula is whatever number we're trying to compare. Okay, so in this example, it says, what is the probability of pulling out a single bag of candy from a production run that weighs less than the lower specification? So I am interested in comparing my bag of candy to the lower specification. So in this case, x would be the lower specification. Let me give you a couple of other examples. What if I said, what is the probability of pulling a single bag of candy from a production run that weighs less than a half a pound? Then what would x be? Okay, take a second and answer that. The answer would be, x would be a half a pound. What if I said, what proportion of the bags that are produced will be smaller than 1.3 pounds? Then what would x be? X would be 1.3 pounds. So x is going to be whatever number that I am comparing my observation to. In this case, we're pulling out a single bag of candy, and we are going to compare the weight of a single bag of candy to the lower specification. And that's given in the problem. So x in this example is the lower specification limit, 0.9560. All right, now the next step is to draw x on your picture. So along the bottom of this normal curve, that's just a number line. So you just draw in x on that number line. If x is less than 0.99, it's going to go on the left. If x is greater than 0.99, it's going to go on the right. Okay, so you draw your picture and draw in x. All right, so now your picture should look like mine. The next step of this is to shade the part of the drawing that represents the proportion or the probability that it's asked for in the question. So let's reread the question. It says, what is the probability that you'll pull a single bag of candy from the production run that weighs less than the lower specification? So which part of this curve will you shade? I want you to think about that and you give it a try, and then I'll show you. All right, you should have shaded the little tail down here, which is less than the lower specification, or smaller than the lower specification. And that little shaded area, that represents the probability that we're going to be calculating. All right, so now we can actually start doing some of the math. So now I want you to calculate z. You've got all the variables, just plug them into the formula and get a number for z. All right, you should have gotten negative 3.4. If you plug those numbers in the formula, you get negative 3.4. Now, in order to find probabilities associated with z, we need to use the z-table. Now, I'm going to tell you, there are lots of different z-tables. You probably used one in your statistics class. There may have been another one that you have seen at some point. The one that we are going to use is the one that I am giving you in the handout. And so that is the z-table that we'll be using for this class. You will be given that same z-table on the exam. So that's the one we'll use. So I'm going to teach you exactly how to use it. In fact, I'm going to teach you how you can use any z-table that you're ever given. All right, so I'm going to give you a minute. Go ahead and pull out the z-table from the class notes. All right, this is what our z-table looks like, and all z-tables will look relatively similar to this. They're all used the same way. They have numbers along the left in the column, and then they've got numbers along the top in that top row. This sort of labels those columns. So here's how it works. When you're given a z value, you're going to begin looking up the z value on the left-hand side of the table. So for instance, in this example, if z equals 1.00 and we're asked to find the probability associated with that, we look up the z on that left-hand column and we slide all the way down until we get to 1.00. So here is the probability associated with a z of 1.00. The probability is 0.34134, which you can see circled here on the table. Now, if the z value is 1.02, we're going to start there where it says 1.00, but then you see the numbers across the top. They represent, the first column would represent 1.00, the next column is 1.01, the next column 1.02, the next column 1.03, the next column 1.04, and so forth. So if we need to find a z of 1.02, we go down the left-hand side of z and we look up 1.00, and then we have to jump 2 columns or 3 columns to the right to get to the column that is labeled 0.02, and that will be the probability associated with a z of 1.02. And here's where it is. All right, now you try one. Now really take your time and see if you can get the probability associated with this. I want you to find the probability from the z-table that is associated with a z of 2.27. All right, did you get it? All right, let's look back at our problem. All right, we have a z of negative 3.4. So now you take a minute and I want you to look up the z value, look up the probability that is associated with a z of negative 3.4. Oh, wait a minute. Our table doesn't have any negative z values. All our z values are positive. Hey, are you going to give us a negative z table to go along with this? And here's the answer. No, I'm not. All right, we have a z of negative 3.4. So now remember, our normal distribution is symmetrical, which means it looks exactly the same on the right-hand side as it does on the left-hand side. So if we're looking up a z value that is positive, it's to the right of the mean. And that's what the z table that we have represents. But if we have a negative z, that just means that our z value is to the left of the mean, and the probabilities are exactly the same because our distribution is symmetrical. So if you have a z value that is a negative number, then you just look up the positive z in the z table, and it will be exactly the same. All right, so you do that. Now look up the z value of negative 3.4, which means just look up the z value of 3.4 in the table and see if you can tell me what that probability is, the probability associated with a z of negative 3.4. All right, so you should have gotten that the probability associated with a z of negative 3.4 is 0.49966. All right, so now I'm going to give you the secret. This is the secret to reading any normal z-table, and it doesn't matter which one you were given. You can always read it if you will understand this. And I'm going to do it for hours. The way that you read this probability, 0.49966, it relates to a very specific part of the normal curve. And every normal table will shade the portion of the curve that represents that probability. So for our z table, this probability, 0.49966, represents the shaded region here. And if you're smart, you'll recognize that this part of the curve is actually on the right. It's to the right of the mean, but our negative 3.4z is on the left of the mean. But remember, the normal distribution is symmetrical. So it doesn't matter if your z is positive or your z is negative, the probability that you look up in the table will represent the shaded region of this normal curve, and the shaded region will be to the right of the center, to the right of the mean if z is positive, and it will be to the left of the mean, or the left of center, if it is negative. So which one of these two drawings that's shown here represents the shaded region of our distribution? Yes, so 0.49966 is the probability that's associated with the shaded region here to the left of the center of our curve. All right, so we just calculated that z is negative 3.4 and that the probability that's associated with z is 0.49966. So now I want you to pause the video, and as a group, I want you to either point to or shade the region of our drawing on this slide that corresponds to this probability. Okay, so the blue shaded region corresponds to this probability 0.49966. But what is our question asking? Our question asks, what's the probability of pulling a single bag of candy from a production run that weighs less than the lower specification? That is the black shaded region. So of course the blue shaded region and the black shaded region are not the same. Now, based upon what you know about the normal distribution, what proportion of observations will be below the average? Can you use that information to figure out what the probability is that's associated with the black shaded region in this drawing? So the area of the curve left of the center is half of the curve, or 50%. course, 50% of the observations will be below the average. 50% of the observations will be above the average. So 50%, half the curve, will be to the left of the mean. So if the entire curve to the left of center is 0.5, and we know that the blue shaded region is 0.49966, how would you find out what the leftover portion of this curve is that represents the probability P? And to find that, we just take 0.5, which is the left-hand half of our curve, and subtract the probability that we know, which is 0.49966, and we are left with 0.00034, which is equivalent to 0.034%. So the answer to the question, what is the probability that we reach into a big bucket of all of these 1 pound bags of candy and pull out a single bag, and that single bag weighs less than the lower specification? It will only happen 0.034% of the time. So here's something to think about. We calculated the process capability, and we found that the process capability for this process is that it's marginally capable. But now when we calculate the probability of actually finding an error or finding a bag of candy that does not conform to the FDA's regulations, we find that that probability is only 0.034%. So is that really that big a deal? Is having an error 3 or 4 1/100ths% of the time, is that big a deal when we're dealing with candy? Well, so what are your thoughts? Well, if there are big fines associated with violating the FDA's standards, then maybe it is a big deal. You know, think about it this way. Approximately 80,000 pounds of M&Ms are produced each day. So that would be 80,000 1-pound bags of M&Ms produced. Well, if 0.034% of those bags were defective, were below the low specification, that would be 27.2 bags every day that violate the FDA's standards. And maybe you might argue that for bags of candy, it's really not that big a deal. Nobody's going to figure out that 27 bags out of 80,000 are below weight. But think about it this way. Did you know that there are about 87,000 airline flights in the United States each day? Well, if there were 87,000 airline flights each day and 0.034% of them were defective or crashed, that would be about 30 flights that would be crashed each day. 30 airline flights that would be crashed. So this level of quality would be completely unacceptable in an industry like the airline industry. All right, let's look at another example. So here's the problem statement. Here's the question. What is the probability of pulling 5 bags of candy out of a production run where the average of the 5 bags is larger than 1 pound? Or another way to ask that is, what proportion of the samples of 5 bags of candy would be larger than 1 pound? And again, I'm asking this question 2 ways here because there are 2 ways that I could ask the same question on the exam. So let's picture what's actually happening. So again, you're standing by the machine and there is a large bin or box of bags of these 1 pound bags of candy. And so you reach into that container and you pull out 5 bags at random and you measure the weights of all 5. You add the 5 weights together, you divide by 5 to find the average, and you're asking, what is the probability that you'll pull out 5 random bags out of that big box of candy and the average of those 5 bags just happens to be larger than 1 pound? Another way of saying this is, well, what if you pulled out samples of 5 bags of candy out of this box? So you pull out 5 bags, you weigh the average of that. You pull out 5 more bags, you weigh the average of that. You pull out 5 more bags, you weigh the average of that. And you keep doing that until you run out of bags of candy. This same question is asking, what proportion or what fraction of the samples that you measure will actually be larger than 1 pound? So those two questions ask exactly the same thing. And here is the formula that we will use to solve a problem where the sample size is larger than 1. So in this case, the sample size is 5 because we are pulling out 5 bags of candy at a time. All right, so here's a question for you. Think about this. What was our sample size in the previous example? So for this example, we have a sample size of 5 because we're pulling 5 bags of candy out of the production run at a time and taking the average. For our previous example that we calculated a few minutes ago, what was our sample size? So in our previous example, we were pulling out 1 bag of candy. So our sample size, n, was 1. Now look what happens when we plug a 1 in for n in this formula. We then get the square root of 1. Of course, the square root of 1 is 1. Taking sigma divided by 1 is the same thing as just having sigma. And look at the formula for z. It's exactly the same thing. Turns out these two formulas are equivalent. The first formula, the z equals x bar or x minus mu divided by sigma, is when we have a sample size of 1, and then the formula there on the top, z equals x bar minus mu divided by sigma over the square root of n, is when we have a sample size that is not 1, when the sample size is greater than 1. It could be 2 or 3 or 4 or 5 or any number greater than 1. All right, let's do this again. Write down the variables that are given for this problem. All right, now you've done this once. I want you to give this a try. Here is the blank drawing of our normal curve. I want you to figure out what number we are going to use for x bar here, knowing what you know from us doing the other formula, and where would we draw that on this curve. So I'm going to give you a minute. First thing you can do, figure out what we're going to use for x bar, and then where are we going to draw that on this curve. So x bar in this formula is similar to the x that we had in the previous formula, meaning that it is the average that we're comparing our sample to. So in this case, the question says, what is the probability of pulling a 5 pound or 5 bag sample of candy out of the production run? And the average of the 5 pound or 5 bag sample is larger than 1 pound. So we are comparing our average sample to the number 1 pound. Therefore, x bar in the formula will be 1 pound. It's the number that we want to compare our sample to. So we can draw 1 pound on our normal curve. It is to the right of the mean in this case, because 1 pound is bigger than 0.99 pounds. Now you figure out what portion of this curve will we shade. In other words, which portion of the curve represents the probability that we're looking for in this problem. So because we are looking to see what proportion of samples will be larger than 1 pound, or what is the probability of pulling out a sample and the average of the sample being larger than 1 pound, we're concerned with that part of the curve that is larger than 1 pound, which I've shaded here. All right, now you calculate z, and you calculate the probability associated with z. Take some time to do this now. Okay, so z is 2.24, which makes sense because z is a positive number, and z in this case is to the right of the mean. It's to the right of the center of the normal curve. All right, now look it up in our z table. You should have found the probability to be 0.48745. So what portion of the normal curve is represented by the probability 0.48745. It is the portion shaded at the top of our z-table to the right of our mean. So you shade this now in our normal curve. So the probability 0.48745 represents this blue shaded region of our normal curve. But that's not what we're looking for the answer for this question. We're looking for the little black shaded region up in the tail of this distribution. So how would we find the probability P, that small tail at the end of our normal curve in this picture? Well, the entire half of the curve from the mean, which is 0.99, all the way to the right is half of the curve, 0.5. Well, we know that the blue shaded region is 0.4875. We know that the entire half of the curve is 0.5. So if we subtract these two, we can find the probability of just the tail, which is 0.01255 or 1.255%. All right, let's do a little mental exercise. We just found out that the probability of pulling a 5-bag sample that has an average weight of larger than 1 pound is 1.255%. So that's the probability of pulling 5 bags out of our bin of bags of candy and weighing them and finding that the average is larger than 1 pound. The probability is 1.255%. So now the question is, if we use a smaller sample size, and by the example I give here is 3 bags, but it could be anything smaller than 5, do you think the probability of the average sample, the sample average, will be greater than or less than 1.255%? So if we take a smaller sample size, 3 bags, 2 bags, 1 bag, will we be more likely that our sample weighs more than a pound, or will we be less likely? And we'll actually calculate it, so we'll know for sure. But let's see if we can think through it. All right, let me go the opposite direction. What if you took an infinite sample size? So what if my sample size was infinity? In other words, I chose a sample size, instead of a sample size of 5, I chose a sample size of infinity, and I measured all of the bags of candy that have ever been made and that ever will be made, and that is my sample size. Well, if I did that, what would my sample average be? Well, the average would just be 0.99, because that's the same as the population average. The population is all of the bags that ever have been made and ever would be made. And if I chose that to be my sample size, then the average of my sample size would always be 0.99. It would never be anything else. It would be very, very consistent. The only way that I get inconsistent averages for my sample sizes is if I choose smaller sample sizes. So for instance, if I chose a sample size of 100,000 bags, then it wouldn't always be 0.99, but it would be something really close to 0.99. I get down to a 5-bag sample, and there is actually a 1.255% probability that the average of that sample is greater than a pound. Well, if I keep reducing the sample size, then the variability of the average of that sample should increase. It should get larger. If I took a sample size of 2, you don't know where those 2 bags are or what those 2 bags might be. It could vary very wildly. So we should expect that the probability of pulling a smaller bag sample and having an average weight larger than a pound would be larger than 1.255%. But we can try it. We can check it out mathematically. We don't have to guess. So let's take a look. In our formula for z, we just put 3 in for n, and all the other numbers will stay the same. When we do this, we find a z of 1.73. The probability associated with z is 0.45818. And we find that the probability of pulling a sample of 3 bags from our bin and taking the average, and the average being greater than 1, is 4.182, which is greater than the probability for a 5-bag sample. So our intuition was right. If we make the sample size smaller, then the probability of the average weight of the sample being larger than a pound increases. Okay, let's talk briefly about an administrative issue. Now, you may or may not have taken a look at your basic function calculator, which you'll be using on an exam, but it's likely that your basic function calculator does not have a square root key, but that is okay. Now, I realize that on these examples, I had us calculate the square root of 5 and the square root of 3, which turn out to be weird numbers. But on the exam, to make this easier, I promise that the only sample sizes that I will give you for calculations such as this will be sample sizes of 4, 9, 16, 25, or 36. And you can calculate the square root of all those numbers in your head. So you will not need a square root button on your calculator. If you have a basic function calculator without a square root button, it is okay, because the only sample sizes that I will give on the exam are sample sizes of 4, 9, 16, 25, and 36, which you can do the square root of in your head. All right, now at this stage, you've probably noticed a pattern, and the pattern so far has been that when we find z, we look up the probability associated with z in the table, and then to find the answer to these questions, we take 0.5 minus the probability that we found in the table. So here's my big warning to you. This is not the correct answer. Not all of these problems are configured this way. I am warning you, please draw the figure, draw the diagram, shade the region that you're trying to find the answer to. Shade the region that's represented by the probability of z. Look at the two and figure out what you need to do, what math you need to do in order to get to the answer. And here we go. Let's do some other examples. And in these examples, you'll notice that the math is different. Okay, I have 3 questions here. Here's what let's do. I want you to pause the video, and I want you to try to calculate the first 2 probabilities on your own. So the first one is, what proportion of 6-bag samples will be heavier than 0.98 pounds? And the other one is, what is the probability of a 6-bag sample being smaller than 0.999 pounds? So pause the video, and if you're there with a group of friends, then try these 2 calculations on your own. And here's my advice to you. Make sure that you draw the drawing of the normal curve that you're trying to figure out first. Draw that normal curve. That is going to be your secret to getting the right answer. Okay, so for the first question, what proportion of 6-bag samples will be heavier than 0.98 pounds? Hopefully you've drawn this diagram. What portion of that diagram should we shade? What portion of the diagram represents the answer we're trying to find? Well, the question asks what proportion of 6-bag samples will be heavier than 0.98 pounds. So that means that we are going to shade the entire region of the curve that is greater than 0.98 pounds. That is to the right of 0.98 pounds, which is really most of the curve. So here you can see I've shaded most all of that curve. All right, so that is the proportion that we're trying to find. That's the answer that we're trying to get to. Now, you calculate z at 0.98 pounds. So where x bar is 0.98 pounds, you calculate z and the probability associated with z. Okay, so z is a negative number. It's negative 2.45, and the probability associated with a z of negative 2.45 is 0.49286. Now, you shade the region of our normal curve that is represented by this probability, 0.49286. So, just like all of our other examples that we've done today, the probability that's associated with z, the probability that you find in that table, is represented in the curve by the portion of the normal curve from the mean, from the center of that curve all the way out to whatever z is. So it's only going to cover a portion of this curve, only from the center out to z. So that's this sort of blue model part of the curve that I created in this drawing. That is the proportion of the curve that is 0.49286, but that's not the answer that we're trying to get. Now look at the overall portion of the curve that is shaded black. That is the proportion that we are trying to determine for the answer for our question. So taking a look at this, how would we find out what the probability is of a 6-bag sample being heavier than 0.98 pounds? How would we find the probability of the entire black section of the curve if we know what this smaller blue section is? Well, to find this answer, we do not subtract from 0.5, we add 0.5. So you see, if we have the shaded region, that blue shaded region, which is the probability associated with z of 0.49286, and we're looking for the overall black region, well, the entire other half of the curve is 0.5. So we need to take that other half, 0.5, and add it to that blue shaded region to get that the overall probability there that is greater than 0.98, which is most of the curve, is 0.99286. So there's actually a 99.286% probability that we will pull out a 6-bag sample and it will be greater, heavier than 0.98 pounds, a large, large majority. So you see, in this particular situation, we do not subtract, we add. So like I said before, make sure that you draw the picture, because if you draw the picture, you'll always get this right. You'll always know whether you should add or subtract. You won't have to guess if you draw the picture first. All right, let's take a look at the next example. All right, just like before, we've drawn the normal curve. We've drawn in the value for x, or x bar. In this case, it's 0.9999. And we want to know what's the probability of a 6-bag sample that is smaller than 0.9999. So now, just like we did in the previous examples, you shade the region of this normal curve that represents the probability that we're looking for in this question. Okay, so here it is, the entire region to the left of z, smaller than 0.9999. Now you calculate z. Now that you've calculated z, you need to shade the region of the normal curve that is represented by this probability that you just found out of the table. So now take the time to look up at our normal curve and shade the portion of that curve that is represented by the probability 0.49224. So if this blue shaded region of our curve represents the probability that was shown in our z table, because the probabilities in the z table always represent probabilities from the center of the curve out to z, So in this case, the center of our curve out to 0.9999. Then what is the answer to our question? What is the probability of pulling a 6-bag sample out that is smaller than 0.9999 pounds? And again, with this example, we need to add 0.5 to the probability we found from the z-table. You can see here that the probability from the z-table is only a small part of the curve. It's only the part from the center out to z. We have the entire other half of the curve that we need to add in. So we add 0.5 to 0.49224, and we find that the probability of pulling a 6-bag sample that has an average weight of smaller than 0.9999 pounds is 99.224%. Now let's look at the third question. All right, here is our normal curve, and here's our question. What proportion of 6-bag samples will have average weights between 0.98 pounds and 0.9999 pounds? So what proportion of 6-bag samples, or if we pull out a 6-bag sample, what's the probability that its weight will land somewhere between 0.98 and 0.9999 pounds? So I want you to first write these numbers in their appropriate spots on this normal curve. So remember, the center of the curve is the process mean, which is 0.99, and you need to write in the other two weights that we're trying to compare to. Now, shade the region of this normal curve that represents the answer we're trying to find. So shade the portion of the curve that is between 0.98 and 0.9999 pounds. So this dark shaded region represents the part of the curve that we're interested in finding out. We need to find out what proportion of the curve is made up by this dark shaded region to find the answer to our question. So think about it for a minute. Do you have any ideas about how we would find out what this shaded region represents? Well, let's see. A few minutes ago, we calculated the probability from the z-table that's represented by the center of the curve out to 0.98, and we also calculated the probability from the z-table that is represented by the center of the curve out to 0.9999. You can find these two probabilities in the calculations we just did a few minutes ago. And so we know what those two are. And now look at the curve that we're trying to find. The shaded region that we're looking for is just the sum of these two separate calculations from the z-table that we made. So once we've done those other two calculations, then this one is really easy. You just add together those two probabilities from the z-table, and we find that together they represent 98.51% of the overall curve. Now, at this point, I don't know how confident you feel about these calculations, but I will tell you, you can watch this video as many times as you want, and I'll invite you, watch it with friends. Work through the examples, work through the practice problems. The instructional assistants will also be happy to walk through practice problems with you or these examples with you and explain them to you again. You can understand this. Put the work into it and learn how to do this. If you can do this, it will really help you to be successful in your careers, because there are a lot of different opportunities that you could have to use math like this. So here are some examples of places where you might use these calculations. You might have historical sales per day, so a mean and standard deviation that are probably taken from a control chart, which you could do. And you might want to know, well, what's the probability that sales would drop below a certain value amount in one day? So for instance, maybe your boss is concerned that the sales have dropped below a particular number and is starting to get upset. You could actually calculate the probability that that number would normally or naturally drop below that particular dollar amount during a day. And you can know that that is that probability and know whether or not you should start getting upset about it or whether or not you should just let the process alone and that the number will come back. Or maybe given historical sales per employee, again, you could track this on a run chart, create a control chart for it. You could calculate the probability that one employee would have sales over a certain dollar amount. So maybe one employee has high sales one week and you want to know, should I congratulate this employee? Should I tell them that they are employee of the year and give them a raise because they're doing so great? Well, you can actually calculate the probability that they would have sales of that value just by doing their normal job, just because of normal fluctuation in their job. All right, here's another example. And this is one that I actually encountered in one of my jobs. All right, so we currently have 10,000 units or 10,000 products in inventory. And given the historical sales per month, a mean and a standard deviation, then what is the probability that the average sales over the next 5 months will average more than 2,000 products a month? So of course, if we had sales of 2,000 products per month over the next 5 months, we would run out. We would have no more products in stock. Now this actually happened to me. So let me tell you the story. We got these certain parts or certain products from a supplier of ours, and it took a while. They had a long lead time to get the parts in, and I wanted to place an order for those parts from the supplier to get them in because I knew that we only had 10,000 products in inventory. Well, I was told by my manager, don't place that order because we still have 5 months of inventory in stock. We've been averaging sales of 2,000 products a month, and we still have 5 months to go. And it won't take that long to get the order from our supplier, so we don't need to order right now. Well, I very quickly knew that the 2,000 products per month is an average. So we've been averaging 2,000 products a month, which means that some months we might have fewer sales and some months we might have greater sales. So in actuality, we actually had a 50% probability of stocking out over the next 5 months. Well, I pointed this out to my boss and I said, you know, what you're doing is you're doing this math off of the average. And if we, instead of being exactly average, if our sales are just even slightly higher than average over the next 5 months, we'll stock out a lot sooner than the 5 months. And we only have a 50% probability of having those products in stock at the end of the 5 months. Well, my boss wanted to know, well, then when do we need to order so that we can be assured that we'll get the products in before we run out? Well, of course, because the normal curve goes out to infinity, you can never keep enough inventory in stock. But instead, I could actually calculate the probability of stocking out at different times. And so I used the same calculations that we've been doing here in class to be able to calculate probabilities for different time periods. And then I gave my boss the numbers and I said to my boss, well, what do you want the probability to be? Do you want the probability of stocking out to be less than 10%, to be less than 5%, to be less than 3%? And if you tell me what your risk tolerance is, then I can tell you when we need to place the order for parts. And so then, of course, my boss thought that I was really smart because I was able to calculate all these probabilities, but it really isn't that difficult. It just involves these simple calculations that we've done today in class. Okay, so this slide you will not be tested on. This is not testable material, but this is just information that I wanted to give to you. You know, we've been doing these calculations with a basic function calculator, but if you wanted to do these calculations in Excel, I wanted to show you how you could do these same calculations in Excel. In fact, how you could create a simulation for a situation and play it out in Excel and test it out for yourself. So in this case, what is the probability that a sample of 4 bags of candy would have an average weight of greater than 0.9995? Well, the way that you would calculate that is by entering in this formula into Excel. This formula is how you represent all of that information. The data in Excel, so this formula gives you what's called the cumulative normal distribution. So what that is it's a z-table inside of Excel, but their z-table shades the curve from the far left of the normal curve, from negative infinity all the way out to z. So in this case, the number given by Excel is 0.82894, which would be the normal curve shaded all the way from the left and all the way out to 0.9995 on the right. That's what Excel gives you. But in this case, this example is asking for the average weight greater than 0.9995. So we just need the rest of the curve. So in this case, we would take 1 minus the number that Excel gives us to find the answer. So you've just got to know a little bit about what Excel is giving you. You can also create a random distribution that would simulate candy production. And so the formula there at the bottom would simulate it. Every time you calculated that formula, it would give you a different number, which would be like you creating a new bag of candy, and you could see what that bag of candy is. So you could actually run a simulation of this. All right, the very next class, class 15, we're going to be doing an in-class simulation and demonstration. I'm going to be trying to demonstrate many of the calculations that we've learned for this section of the material to help prepare you for the exam. And we'll be doing it in the format of a simulation in class so you can actually see how it would work. So if you'd like to participate in the simulation, bring your laptop. It is optional, but it'll make it a lot more fun if you do. There will be an Excel file that's posted in the class notes. Just bring that Excel file on your laptop and you'll be able to participate in that simulation. I also want to encourage you, please practice the practice problems on Blackboard. Make sure that you feel that you are doing really well in the calculations for calculating probability, for calculating control limits, for using control charts, because the material we'll cover on class 15 is going to be mostly a review, and I just won't have the time to start from the beginning and to reteach you how to do all of these calculations. I want you to have practiced a lot before you get to that class. If you can do this, then this class really will be a great review for you for our exam. Now, there's also an assignment for your project groups that is due by class 15. So you're going to need to turn in your process improvement project goals, which include both quantitative goals regarding the time that your process takes and the number of steps that your process takes, as well as qualitative goals. So things that you would like to see your process, ways that you would like to see your process perform differently. You also need to turn in your team's ideas for improving the process. So what are your ideas for improvement? What are some things that you would like to try to do? If you're very detailed about your process improvement ideas and explaining those to me, then I can give you some really good advice that is going to try to make the outcome of your project a lot better. I'll be able to tell you what might work, give you some ideas about some additional things that you might try, or some other things that maybe you haven't thought about. But you have to put the thought into it first and be very detailed in the descriptions that you give me for this project milestone. There's a Dropbox located on Blackboard, and the details of that assignment are listed there. Please read those before turning that in. Also, during class 15, you're going to have an individual assignment. It's not really a graded assignment. I just want for you to be able to report on the progress of your team working together. So I want you to grade each of your teammates on their participation and engagement at this part on working on the project. Now, If you grade your teammates lower than 100%, you need to justify that. In other words, you need to explain why that is, why you're giving them a grade that's lower than 100%. Honestly, most teams will perform really well and will work together really well, but every now and then you end up with a team or two that has someone on the team that is not participating fully. There are peer review sheets that are available on Blackboard, and so you just print that out, write down the names of the people that are on your team, and give them each a grade in terms of their participation. Like I said, for most teams, everyone gives one another 100%, but this is an individual assignment. You do not need to share your ratings of your teammates with your group mates. You can do this individually and privately, and then I'll have a Dropbox in the classroom that you can turn this in when you're here next class. And then here is our final thing as we look forward to the next few classes. So class 16 is our second exam, and it will be covering control charts, process capability, and these probability calculations that we did today. So you'll have practice problems. You should be well prepared for that exam. After the exam, quiz 9 is due by 10 a.m. prior to class 17. And that just involves reading a case that I'm going to be putting on Blackboard. Don't do that now. I'm not going to post it until after the exam. But after the exam, you'll read that case, and just as long as you've read the case, you're going to do very well on that quiz. I just want to make sure that you've read the case before our next class after the exam so that we can be prepared to talk about it together. Also, after the exam, there's also an opportunity for another extra credit assignment. If you'd like to do another mini Kaizen or a little 2-second lean, a little fix what bugs you video this time, it does not have to be a paper, just a video. Again, this is an optional assignment. You do not have to do it, but if you'd like the opportunity for extra credit, you'll have a Dropbox. There's instructions that are available on Blackboard for you to do, and I look forward to looking at those. And then I have a note on here as well about your next project milestone after the exam, just so that you can be prepared for what is coming up next. Make sure that you practice the practice problems, and I'll see you next class.